we are now going to continue our discussion of covalent bonding. So we've talked about a few different things, but one of the big ones that I want to discuss now for the remainder of today is the concept of expanded octets or hypervalency. So if, for example, where are we? I ask you to draw a Lewis diagram for this compound, SF6. Now, the only way that, so if we could still follow all of the rules for Lewis diagrams, right? So we'd say, all right, well, sulfur goes in the middle, probably, and then we have the fluorine. That's a lot of electrons, but at this time, we can probably not, it's not charged, so if we jump the gun a little bit, right, we could say, well, I have sulfur, and I probably have, you know, all the fluorine atoms around it. And then I put in all my electrons. And I probably get a structure that looks like this. What's wrong with this? In this structure, sulfur has an octet of 12. 2, 4, 6, 8, 10, 12. Yikes. So now the issue of what we would call expanded octets or hypervalency is a complicated one, and a lot of the actual complication is sort of besides the point for us, but I'm going to highlight it a little bit. So the first series of kind of arguments about how this kind of bonding occurs allowed for what we would call an expanded octet or hypervalency, and for some elements. And the reason for this goes back to quantum numbers. So the valence of sulfur is, well, if we look at so the sulfur is under oxygen, right? So it's going to be 3s2 3p4, right? Which in principle means sulfur should only really have a bonding arrangement similar to that of oxygen. So 2 lone pairs and 2 bonding pairs for a total of 8 electrons. But we do see compounds like this existing. And the initial understanding of this was that, in fact, what's different, say, between sulfur and oxygen is this, right? So we know, for example, in the case of oxygen, where the valence is n equals 2, that there are only access to 2s and 2p orbitals. But in the case of sulfur, the valence is in 3. And in the case, if n equals 3, right? So if n equals 3, L is allowed to be 0, 1, and 2. So we are allowed to have, what are we allowed to have? We're allowed to have 3s, 3p, and 3d, even though the sulfur atom itself doesn't have any electrons in the 3d orbital. They are allowed to exist. So that means for us, the idea here was that maybe this bonding arrangement puts electrons in those empty 3d orbitals so that we can have this expanded octet. Now, a lot of sophisticated work has been done to this end, and has done lots of calculations, all kinds of experiments. And it turns out that that's probably not what's happening, right? That the 3d orbitals don't really participate in the bonding. So what's really going on? And it turns out that the best model for something like SF6, the most accurate model, is one in which we have this going on. It's a very complex resonance situation where I'm not going to draw. There's like a bunch of different possible resonance structures. I'm not going to draw them all, but you can get, hopefully maybe you can get the idea, which is there are basically 6, I guess, resonance contributors that we could draw where some of the fluoride ions fluorines are actually fluoride ions, and that the sulfur is 2+, and that the hybrid looks something like this. So each fluorine actually carries a charge of -1/3, and the sulfur is 2+. Now, what's happening in these situations is that not that we don't understand what's going on, it's just that we're coming up kind of against the limitations of the Lewis model. And that's okay, because the thing is whether or not we draw it like this or we draw it like this, ultimately what we really want to know at our level is how do the connections of the atoms explain their arrangement in space, which is what we're going to start talking about later, right? The geometry of these molecules. And so it's really important, that part of it, whereas the specific details of how the bonding actually happens is really too sophisticated for our level. To be honest, I find it fascinating, but you know, it is very, very complicated. So the rule of thumb for, and I'll be honest, there's continually ongoing discussion in our department about how we should be handling hypervalent compounds in our lectures and in our testing, and we try and walk a middle line. But the general rule of thumb is that compounds where their valence electrons are in n = 3 or bigger, all right? So this means things like sulfur or phosphorus could be hypervalent, for example, or chlorine could be hypervalent, but definitely not something like nitrogen or oxygen or fluorine, or carbon. Those definitely cannot be hypervalent. So we have to watch out for those. So let's look at some examples. I gave you guys, I think, this came from a worksheet that I think I distributed to you guys a while ago. So we did SF6. So let's look at something like PCl5 then. So again, if we look at the number of electrons, so phosphorus has 5 and each of the chlorines has 7. So, right, so I have P, and then I have my chlorines. I'm going to cheat here. Tab, go ahead. Yeah. Yeah. Well, so here's the thing. This one here, this is the one you're talking. This one is actually not hypervalent. That's the thing. This is the model that is proposed to say how do we get around the fact that you'll see when we start talking about geometry, we need to be able to explain the shape of this molecule. But it seems that from everything we know about quantum mechanics and the way orbitals overlap, that hypervalency isn't actually a thing. All right. So this is the model that they use because this version, right, the version that I drew before, right, where it's all covalent bonds, in this version, the sulfur is hypervalent. Well, but the Fs are never hypervalent because if you count the electrons, they have 8, right? So it's in this version, the sulfur is hypervalent here, right? Now, the sort of the hardcore theoretical chemists, how about that? They really don't like this because for them, hypervalency isn't a thing. It doesn't exist. So this is the model of SF6 that they propose to explain both its shape, again, which we'll talk about a little later, and the way bonding works. And it's actually pretty true, is that these bonds do definitely appear in terms of the length and the strength and all that. They do appear to be this mixed, somewhere between polar and almost ionic even. But if what we're really concerned about is the geometry and how this geometry exists, we are going to stick to using these hypervalent structures because they're a model, right? And we always have to keep in mind that no matter what we're doing when we're drawing stuff, is that we are creating models of reality. And if the model suits our needs, then it's acceptable. All right. We just have to be conscious of the fact that it isn't real. It's a model. Okay. Sometimes you can think about it in terms of how the frame of reference that we're using for at our stage of the game. Our frame of reference is going to be the overall way in which the atoms are connected to each other, and then ultimately how this impacts their shape, right? We're not worried so much about the exact details and energetics of the bonding. That is much more sophisticated. I don't know. So I can give you a physics sort of analogy, right? So in mechanics, you guys study like Newtonian projectile motion, for example, right? And the truth of the matter is that if I throw a ball, not only is it following that Newtonian curve that I can do easily on paper, it's also moving with the rotation of the Earth and the orbit of the Earth around the solar system and the orbit of the solar system inside the galaxy. But my frame of reference is the ball moving relative to me. All right. And so here we're just adjusting the way we're looking at it to suit our needs. But what I want to point out is that it is actually more complicated than that. That's all. Just I want you guys to be aware of the complexity. What about something like sulfate? So the sulfate ion is one that comes up a lot in chemistry and biology, biochemistry. So sulfate, so the sulfur has, like oxygen 6, the each oxygen has 6, so that's 24, and 6 is 30, and 2 more, so 32 electrons, right? So typically, when I've only got one of something, that's the one that goes in the middle. Also, the idea, remember that the least electronegative element generally goes in the middle unless it's hydrogen. So my sulfur is going to go in the middle with oxygens around it. 1, 2, 3, 4, 5, 6. And in this case, one of the ways that we can start actually drawing this right off the bat is, say, just connecting. We know all these things are bonded to each other, and now we can add in the rest of our electrons. So we could say, so that's 2, 4, 6, 8, 9. Just completing the number of electrons that each atom should have. And then the sulfur should have 2 more. And I have 2 extra electrons to add, and those should be added to the two oxygen atoms because they are more electronegative. So remember, when we have a negative charge, we're going to remove electrons from... we're going to add electrons to electronegative elements. So in this case, we're going to add, let's say, this one and this one. So here I have a situation where, well, let's see. So first off, it's a little tricky because I have some unpaired electrons, right? And definitely some incomplete octets. And so if I think about how this would work, there's a few different possibilities. One possibility is that these electrons here on the sulfur get redistributed so that the structure looks like this. Now, the sulfur has an incomplete octet in this case, but very often incomplete octets are not as bad as as expanded octets. And if we look at, actually, that's not true. If we look at this, the sulfur has an octet 2, 4, 6, 8, so that's fine. And each oxygen here has a complete octet. Now, if we count for formal charge in this case, the sulfur has 1, 2, 3, 4 electrons in the formal charge counting. It should have 6, so the sulfur is plus 2. And then each oxygen has 1, 2, 3, 4, 5, 6, 7. So each oxygen is minus 1. Now, overall, this is okay, right? Because the sulfur, the whole thing then is minus 2. And everything has a complete octet. But we can think about this in terms of expanded octets and say, well, what if if we allow for the expanded octet in sulfate, so that, for example, each of these oxygens shares an electron with sulfur so that we form multiple bonds. Right? Well, now the formal charge on the sulfur is 0. The formal charge on these oxygens is also 0, and these are minus 1. And so the whole thing is still minus 2. But this one, in this one here, the sulfur is hypervalent. And again, that's okay. If you look in a biology textbook or in your chem textbooks or wherever, you're going to see that sulfate ion is often drawn like this. All right. And that's because there's a lot of stuff that we can explain in terms of how sulfate ion behaves chemically that seems to make a little more sense when we draw it this way. Again, not at our level. We don't need to worry about it. But the key is that if ever I need you to draw a sulfate ion, either one of these is acceptable to me. All right? It's really, they are okay, because there is some confusion or some, we're dealing with models here.